Welcome all to another session on line commutated and PWM rectifier course. And today we will discuss about multipulse rectifiers. So if we see the total course structure, we are in week 2 and we are going to primarily look into this aspect today, 6 pulse and 12 pulse rectifiers and different types of transformer configuration, and also the input current analysis. Okay, we have already covered the THD and power quality issues in the previous lecture, and we are going to focus more on one of the solutions today to improve the power quality issue. So the solution that we are going to talk about today is basically this one, multipulse rectifiers. Okay, and this is a cheap solution, and it consists of basically transformer and usually diode rectifiers, although active front end is possible, but usually it consists of transformer and rectifier arrangement. But here the improvement in the input current, the harmonic improvement in the input current is done through some special transformer arrangement. The reason why we are studying this is because as part of this rectifier thing, as I told you repeatedly, one must remember the input side also, input power quality also. And this solution based on multipulse rectifiers is one of the most economical solution. It's a cheap and easy to fabricate, and it is and this technology based on rectifier and transformer is a very well established technology. And that is why in many of these applications, industrial drives, for example, we repeatedly see the use of such kind of multipulse high power converters or high power rectifiers. Okay, where these industrial drives have an input AC. So we'll talk about it. Let us go ahead. So many converters. So let us see what is this. We have seen this 6 pulse rectifier. So many converters require a DC at the input, right? For example, not only these motor drives need an DC. Suppose, how does the motor drive, induction motor or synchronous motor drives operate? From the grid. So there is a grid. So for example, let me draw it. So this is the grid. Okay, and then you generally have a transformer, right? And then we have a rectifier here. Okay, and after the rectifier it forms the DC link. Okay, and after this we generally have the inverter. Okay, generally this is the inverter, this is the rectifier, and then we can have a motor drive here, for example an induction motor drive, right? We can optionally also have filters at various places. For example, we can have an output filter here. Okay, output filter. This output filter basically improves the output of this inverter. Inverter output is the PWM switched waveforms, and we try to kind of like make it a little bit sinusoidal, and we also try to control the rise time and all those. So we use an output filter, but many times we also use an input filter. Okay, here input filter to improve the current which is being drawn. Okay, so often this is also used. So this is a typical arrangement of an industrial drive. And 6 pulse rectifiers have been a very popular choice for this. So this rectifier very often is a 6 pulse rectifier. 6 pulse rectifier means a 3-phase diode bridge rectifier. Usually it may be a thyristor based rectifier, but thyristor rectifiers are now getting obsolete. Okay, so generally we use the diodes here. Okay, so this is a 6 pulse rectifier, and it is available for a wide range of voltages and power. Okay, so it is a very popular choice. And if you see the output voltage profile of this converter, so we have here drawn the diagram of this 6-pulse rectifier. Here you can see, here is the grid, then you have this transformer, and then you have the rectifier, 6-pulse rectifier or the bridge rectifier, and then I have used a constant current load so as to emulate kind of a motor load, heavy inductor at the output. But the analysis which I am going to present today is equally valid if you have a capacitive load also. For example, in place of this one, we can also have a capacitive load with an equivalent load resistance. It is also possible. Okay, now how is the output voltage waveform? How does it look like? Typically, as you know, this consists of this 6-pulse rectifier output. So which means that we have 6 lobes here in one cycle. Okay, so here is this one cycle which I have drawn, and there are basically 6 lobes in the output voltage. So we can find out how much is the peak to peak ripple in this output voltage, because this is the function of the rectifier. Rectifier convert the AC into DC, and so we are getting a DC, but we have a ripple. Okay, and how much is that ripple? The ripple is basically, so if you take this as 1 here, and so this angle you can see, because there are 6 pulses, so this angle is basically 60 degree, right? 360 by 6. And so therefore this angle here is basically equal to 30 degree. And so therefore if this, and this is part of the cosine wave or sinusoidal waveform, so this is the peak of the AC waveform, and the nature of this waveform is sinusoidal. So which means that if I take this as this point is 1, this point here will be of course equal to cos 30 degree, which is 0.866, right? So which means, so this is what we have written here, 0.866, and so we say that the peak to peak ripple is almost like about 14% in this case, right? Output voltage. So this is one side. Okay, so this is where this is the output. So if we look into the output of the rectifier, which is available here, okay, this is the V0 output. What about the input? This is where the problem starts. Okay, the input current, as we have covered in some of the previous lectures, is that this input current, right, IA, this current here is a quasi square waveform, and this is going to be a problem which we know, and it leads to poor power quality at the input, like input current harmonics, and some standards like IEEE 519, it will not allow you to use this equipment in your factory or in the real setup, because it is violating this standard and you are drawing or injecting too much of harmonics into the grid. So this standard says that the total harmonic distortion, THD, okay, so the THD should be less than 5%. This is one of the standards which we said. Okay, so now then what is the solution that we are proposing now? The solution is to use, one of the solution is to use a multipulse rectifier. We will see other solutions as we progress on the course, right? We will see if I use a voltage source converter at the front, it can also improve the power quality issue. Okay, but you can also use other single phase. For single phase, we can use like totem pole PFC and all others, which we will see one by one, the input side. But one of the solutions that we will see now is like a multipulse rectifier. Okay, so what is the main advantage of multipulse rectifier? Number one is that it improves the input current harmonic distortion, so which means that the THD will go down. Okay, so that is one of the advantage on the input side. But it has also another advantage, and this advantage is that the output DC voltage ripple of the rectifier gets reduced, right? and so which means that the output voltage is now getting closer and closer to the DC, okay, pure DC. Okay, this is what we expect, right? Ultimately this is a rectifier. We want to convert AC to DC, and the better is the DC, the better is the output, right? So the ripple, if the ripple on the DC goes down, we just saw that the ripple with a 6 pulse rectifier is 14%. If we get it much lesser than this, it is beneficial for us. And at the same time, so there are two benefits happening. One is on the rectifiers, one is on the output side where the ripple is going down, and the other one is also on the input side where the input current also distortion is minimized. I would also like you to look into some of this product brochure of some of the companies. For example, this is coming from the company Danfoss, and there is some link which I have given from Siemens. So these product brochures, or if you search in the internet, you will see many literatures available from these companies. And what do they say? You can find out, you can see, for example, Danfoss is an electric drive company, so they make motor drives, and typically in their applications they use at say medium voltage or high, medium power levels, they typically use this kind of rectifier and inverter arrangement. The rectifier is generally 12 pulse rectifier, which we are going to talk about. So 12 pulse rectifier with a neutral point clamp converter, which is very common in use, right? So Danfoss uses this. Similarly, Siemens has these what is commercially called as the perfect harmony, and this Cinemix perfect harmony, and this has like extended delta connection at the input, and it has kind of like cascaded edge bridge structure at the output for medium voltage applications. So I would request you to go through some of these product brochures and also search in the internet where you will get a lot of information on how these kind of multipulse rectifiers are commercially used. They are very much used in real life. Now let us see the star delta 12 pulse transformer. Okay, so this is the first or this is the solution that we are going to study in details today. So what is there in a 12 pulse transformer? As we see here, there is one primary, okay, which is connected in star here, and there are two secondaries of a transformer. One is in star and another one is in delta, right? So there is a star delta transformer at the secondary. These are connected to the two diode bridge rectifiers, and then their outputs, this is the output, are series connected, okay. And then this output is kind of like fed into the load here. Fine. Now one of the things that you should note is that there is a particular turns ratio of these transformers. If you can see here, N1 is equal to 1 and N2 equal to 1. So which means N1 is to N2 is 1 is to 1, okay, for the star connected arrangement. However, N3 is equal to root 3. So the turns ratio between the primary and the delta is 1 is to root 3, right? And so this is something which we must keep in mind when this thing is going to operate. Now, each rectifier is going to produce a 6 pulse or 6 lobe wave. So for example, if you see the output of, say, this is suppose the V01 and this is V02, you will see that this V01 is something like this, okay. This waveform is which we just saw few slides back, that the output of the one rectifier is a 6 pulse waveform, right? Now the output of the second rectifier, so suppose this is V01 here, right? This is V01 and this is V02. So we can say that this is basically V01. So instead of writing V0, we can write V01 here, correct? So this is the output of the first rectifier, which is connected in star. Now what is the output or what is the waveform of V02? Here we have to be a little bit, you have to understand that this delta, the delta winding on the one of the secondaries causes a phase shift between the line voltages, right? So which means that if we observe the line voltages on the primary side and the line voltages on this here, okay, right, then they are in phase. However, the line voltage of the delta, so these 2 points, if we look into carefully, then there is a phase shift, because we know the delta winding causes a phase shift between the primary and the secondary here in this delta transformer. So this waveform, this line voltage will either have a plus 30 degree or minus 30 degree phase shift, okay, at the line voltages there, correct? Because there is a 30 degree phase shift between the star and delta, and that is why we often use this kind of arrangement, YD1 or YD11. Okay, those who know about transformer connections, they know that there is a phase shift between the primary and the secondary of 30 degree here. So therefore, if we now plot V02 on this waveform, what will we see? So let us plot that. So since so this is 30 degrees, so this is 60 degrees, so which means, right, so this waveform of V02, we are going to plot V02 will be something like this. Note that this is 30 degree phase shifted from the first one. Okay, so both the waveforms are identical. The blue one, so this is V02, right? Both the waveforms are identical. However, there is a 30 degree phase shift between V01 and V02, correct? Because of the delta connected transformer, which causes the phase shift. So when these, so we have now, you can see here, we have now added V01 and V02, and therefore the total V0 that comes up is the summation of these two waveforms, and I can now draw the two waveforms here, and this value, if you just go on adding, so this we are going to add the two waveforms, and it will be something like this. You will see that this waveform is like this, right? So basically you will see that there are now, this you can do yourself, you can do the verification yourself, right? And okay, so it is a sum of these two, and this will contain 12 lobes or pulses. Okay, so when we add them, so we get a 12 pulse rectifier. Okay, when you add one by one each of these waveform, you get a 12 pulse waveform. Okay, so the output, this is the V0 waveform, right? V0 waveform is a 12 pulse waveform, right? And this is what the output voltage looks like. And if you see it carefully now, that because there are 12 pulses which is spanning over a 360 degree, so the width of each of these lobes will be equal to 360 degree by 12, which is 30 degree. So which means that if this point is 1, this point here will be cos 15 degree, and cos 15 degree is roughly equal to 0.96, right? This is what is written here. Okay, cos pi by 12 and 0.96, and so therefore the peak to peak ripple here is now about roughly approximately 4%. Okay, so we see that the output voltage of 12 pulse rectifier is definitely much better than that of a 6 pulse rectifier. In 6 pulse rectifier, the ripple was about 14%, and in 12 pulse rectifier, the ripple went down to about 4%. Okay, so definitely we are making a better quality of rectifier when we use this kind of a transformer arrangement. But there is an additional benefit, okay, and that benefit comes from the input current, which means that this current is actually will get better when we use a 12 pulse transformer, and that is what we are going to see now, how the IA current actually is getting better. So in order to understand this, there is a little bit of analysis involved on how to draw or how to know what is the current IA. Okay. Now, in order to understand this current, we have to use some of the basic principles of transformers and the MMF balance in a transformer. So you can see here, this current IA, right, is basically equal to the reflected secondaries currents, right? So there is this primary and then there are two secondary currents. Now, so because this, if we first see the star connection, star secondary, this is the star connection and this is from the delta. This term is coming from the delta. Okay, so I capital A is nothing but, because we have an N1 and N2 equal to 1:1, so I capital A is IAS as coming directly from the star. Okay, N1 I1 is equal to N2 I2 MMF balance, and so therefore I capital A is equal to I small as. And what about the delta contribution? So this delta, okay, so this current here, okay, will have an MMF balance with this IA current, there IA dash, right? But now you have √3 factor that will come into the picture, because this current is this turns ratio is √3, right? So therefore N1 I1 is equal to N2 I2, so N3 IA dash, right? N3 IA dash N3 IA dash will be equal to N1 IA, and therefore when you reflect this current, right, so therefore will be equal to N3 by N1 into IA dash will get reflected, so IA reflected, and that is what I have written here. This is coming here, okay, N3 by N1 times IA dash, right, which is √3. So therefore if I, so the total current I capital A is IAS plus √3 times IA dash. Similarly, from symmetry we can also say IB and IC are exactly similar to it, right? Now let us see what is this current, this IAD current. Okay, let us find out this current. Okay, now by applying KCL here at this point, so let me rub this thing. So if I apply KCL at this point, we can immediately see that IAD, this current, is sum of IA dash and minus of IC dash, right? Similarly, IBD and ICD are similarly. So we do a little bit of mathematical manipulation, and we subtract 2 from 1. Sorry. And we subtract 2 from 1 here, and so we get IAD minus IBD as this value here. Now we can assume that this is a balanced three-phase system, so IA dash plus IB dash plus IC dash is equal to 0. Okay, so we can assume this condition to be true. Most of the time this is true. This is not true in case of an unbalanced system, right? So IA dash plus IB dash plus IC dash is equal to 0, right? And this is the internal current of the delta. And so substituting 5 into 4, what we get is that IA dash, this current IA dash we are trying to find out is IAD minus IBD divided by 3. Okay, so basically we are expressing the these currents IA dash with respect to the delta output currents. Okay, that is what we tried to express here. So we get IA dash, IB dash and IC dash. So these are the currents which are flowing. Now after we have obtained these expressions of the currents, we can say that the input current of the transformer is I capital A is IAS plus √3 IA dash, where we have already got these values of the current IA dash, IB dash and IC dash. Now what we will do now here is to plot these currents, right? We will plot these currents and see what is the IA waveform. This is what we are trying to get into. Okay, we are trying to get this input current waveform. We are trying to plot this current and see its property, right? So at first we are going to plot this IAS current, and you can see IAS is a quasi-square current, right? We know the diode bridge rectifier, the input current is a quasi-square. Next we plot the IAD, this current here, IAD. This is also a quasi-square current. However, this current is 30-degree lagging, right? Because of the delta connection, right? So IAS and IAD are identical, but they are phase shifted by 30-degree. Since IAD we have drawn, we can also draw IBD, because IAD and IBD will be 120-degree, IB will be 120-degree phase shifted. Okay, so this is 30-degree phase shift, and then we have the 120-degree phase shift, right? And so we'll be able to draw IBD, which is 120-degree phase shifted. Now we have already found out what is the expression of IA dash. IA dash is IAD minus IBD divided by 3. So we have got IAD, we have got IBD, and we will divide by 3, and therefore we will be able to now draw IA dash waveform. And you can see here the waveform of IA dash, and you have to also see the amplitudes here. You have to be careful about these amplitudes. Okay, it has a DC component which is 0, but the amplitudes we have to be careful. Okay, this you can just do it yourself also by hand, and you will get these amplitudes. Okay, the different levels of the waveforms. Okay, the levels. Now once we have got IA dash, right, so we can plug in into this equation here. Okay, so we plug in IA dash here, and we have got IAS here. We plug in these two values into this equation, and therefore we will be obtaining I capital A. And when you do this exercise, you get this I capital A waveform, which is shown here. Okay, and also note the magnitudes of these different levels. Okay, these magnitudes are important. Okay, now this is the waveform for the 12 pulse rectified input. So this waveform is actually completely different from this IAS waveform. Okay, so you can understand that because of this 12 pulse arrangement, okay, the waveform, input current waveform has completely changed. If there was no 12 pulse, so suppose if we had only a 6 pulse rectifier, right? So suppose we didn't have this thing at all, right? We had only 6 pulse, then this was the input current in that case, right? And this was very rich in harmonics. Okay, it has all the odd harmonics, 1, 3, 5, 7. It was very rich in harmonics. But now with this 12 pulse arrangement, now we have got this one. So our input current is actually completely changed. We have now this as the input current. Okay, now the waveform has completely changed, and then therefore we will now analyze what is the harmonic content, or what are the different magnitudes of harmonics, which are the harmonics present, which is the harmonic content of this waveform here. Okay, let us do this. In order to do this one, what we will do here is that we will split this into 3 parts, right? And we will then add the 3 parts. So here you can see how I have split the waveform. Okay, so this is here is the blue part. Okay, so basically we are splitting it into this part. So this is one part here, okay, this part and this part here. Okay, and this is basically a square wave. Okay, and this can be drawn directly here. Okay, so this is one part. Now note the amplitude. This amplitude this is ID by root 3, and I have drawn it ID by root 3 here. Okay, so this is the base part of the waveform. Next we have the YOLO part, right? So we have this YOLO part here, this YOLO part, and this YOLO part. We will take it out, and then we can draw these YOLO parts here. Okay, And note again the amplitudes. See here, this is ID. You have to be careful. Here is the ID waveform, right? So because this you see here, this is 1 plus 1 by root 3 and 1 by root 3. So this amplitude here, this amplitude is 1, right? This amplitude is 1 here. Okay, so this is how this ID waveform is drawn here. And then we have the last part, which is this one, the green part here, and this we take out and put it here. Okay, and then we will add the harmonic content. So let us see what are the harmonic contents. We have to recall what we had done with Fourier analysis, a few lectures, Fourier series analysis a few lectures back. So what did we know? We found out that in a square wave, okay, the harmonic, the magnitude of the harmonics can be given by this expression 4id by root 3 n pi sine n omega t. This you can, we have derived it previously. So this is the amplitude. So basically 4 into I by n pi and sine n omega t. In this case, this I is equal to id by root 3, and that is how we got this expression here. Okay, so this basically this square wave has all the odd harmonics. Okay, 4id by root 3 n pi sine n omega t, right? Now what about the second waveform? What are the magnitudes of the harmonics? The second waveform, again, because of the symmetry, odd symmetry and all, it will also have only the odd harmonics, right? 1, 3, 5, all these things. And so this expression will be 4id by n pi and cos n pi by 6 and sine n omega t. Okay, so this is the expression for this one. So here this n pi by 6, cos n pi by 6 is coming because the break in this waveform occurs, or the discontinuity occurs at pi by 6. Similarly, this is another quasi-square waveform and the break happens at pi by 3. So therefore 4id by root 3 n pi, like this, and then cos n pi by 3 here. Okay, this you can just verify. So these are the magnitudes of the harmonics which are present in the different parts of this waveform. Okay, so these are the three parts, and 1, 2 and 3, which are parts of this waveform. And so we can then, the total harmonic content is f1t plus f2t plus f3t, and will be something like this. Okay, so therefore now let us put the values. Put n equal to 1. Okay, if I put n equal to 1, and in this expression we get ft equal to 4 root 3 id by pi into sine omega t, right? This we will directly get. Now if you put n equal to 5, okay, what will you get? So you will get 1 by root 3 plus cos, okay, 5 pi by 6 plus 1 by root 3 cos 5 pi by 3. So what is the value here? So 1 by root 3 Okay, so here you can see that when you put these values here, this value will come out to be, if you put n equal to 5, the value will come out to be 0, right? So this, when you put n equal to, so for the fifth harmonic, the magnitude is equal to 0. Similarly, if you put n equal to 7, again you will see that you can just put n equal to 7 in that, and you will see that ft is equal to 0. But this is not true for n equal to 11. Okay, if you put n equal to 11, you get a value, and that value is equal to this one, okay, sine 11 omega t. Note that the magnitude of the 11th harmonic is 1 by 11. So this is 1 by 11th of the fundamental. Okay, this is important, right? So what we are getting with this 12 pulse transformer is that we are eliminating the 5th and 7th harmonics. That is first thing that we are able to see. But the next harmonic, which is coming at 11, has an amplitude which is only 1 by 11 times that of the fundamental. Okay, this is very important. So we have eliminated some harmonics, and the amplitude of the 11th harmonic is also very low. Okay, so therefore we can say that the 12 pulse rectifier substantially reduces the harmonics in the input current. Okay, so harmonics present in input current at 11, 13, 23, 25, and in general 12n plus minus 1 harmonics are present. Okay, so 5th, 7th, 17, 19, these harmonics are all gone. Okay, and you should also note that the harmonic cancellation in the input current occurs due to the corresponding harmonic flux in the transformer core. Okay, so basically the cancellation of harmonics is happening in the transformer core only, because that is where all these currents and the corresponding fluxes are getting added up, and some of these fluxes, the harmonic fluxes, are cancelling each other, and that is why the input current does not contain these harmonics in this. Okay, so therefore we can say that the 12 pulse rectifier has an input current which is 11, 13, 23, 25. In general 12n plus minus harmonics will be present at the input side. Okay, and there is one simulation here which you can see here, which is very similar to what the waveforms show. So IAS and IAD has been shown here, and these actually contains the 5th and 7th harmonics here, you can see. But when you go to I capital A, right, you can see that this is the fundamental, but then this 5th and 7th, these harmonics are totally gone, and we have 11th and 13th harmonic present in the input current, total input current. Okay, now so this concludes what is a 12 pulse transformer. In many cases we actually try to improve the harmonics further. So with a 12 pulse transformer, often with a low value of inductance, we may not be able to always kind of like maintain the THD less than 5%. Sometimes the THD can go more than 5%, 7-8% it can go, 12 pulse transformer. So we will be able to use even higher pulse rectifiers. Okay, so this is a little bit advanced, and in that case, so suppose we use 18 pulse rectifier, 24 pulse rectifier, 48 pulse transformer rectifier. So this is not transformer plus rectifier arrangement. Okay, and this is a little bit an advanced slightly, so we take it up at a postgraduate level. Okay, so we were not going to cover this one. Actually, this has been covered in one of my other lectures, high power converters, which is also available in NPTEL YouTube, and you can get it in NPTEL YouTube, right, where we have talked in detail about this multipulse transformer. Okay, you can go through it, but basically these kind of higher pulses are used in high performance drives, or it is in many cases used in high voltage DC transmission, HVDC transmission, okay, from where these concepts have come. So there we use zigzag transformer or an extended delta transformer. Okay, so I'll just show you one of this kind of like very high performance drive, okay, which is made up of like cascaded edge bridge. But what is important here is this is the zigzag transformer arrangement, zigzag transformer with a rectifier arrangement. Okay, what it's done here is a zigzag transformer can produce a particular phase shift as desired by the user, phase shift between the input line voltage and the output line voltage. So if you see here, this zigzag transformer, there is this input line voltage here, and then there is an output line voltage. Okay, and this angle here indicates that there is a phase shift between the line voltages of the input and the output. So this is the input and this is the output, and the phase shift between these two line voltages is minus 24 degree, which means the output is like lagging the input voltage by minus 24 degree. And this is done by kind of like cutting the winding of a conventional transformer and rewinding it in a different fashion. This is covered in that other course where I have talked about it in details. I'm not going to talk about it in detail, but here you can see that you can have other types of phase shift like minus 12 degree, 0 degree, plus 12 degree, plus 24 degree. So you can have actually the output voltage shifted with respect to input. Okay, this not only improves the output voltage quality, but it substantially improves the input current quality as well. Okay, so this improves a lot. So this improves a lot. Okay, and the input current become like very close to sine wave. Okay, and you are well within the IEEE standards and like this. Okay, so this way if we look at it, okay, this is another solution. There is also something called as extended delta connection, which again we can see here in the other lecture, extended delta, which is also used to kind of like improve on the profile of the input current. Okay, so with this we conclude the thing of multipulse transformer, and and this is one of the easy to understand and easy to fabricate, cheap. It's a very cheap solution because you just have to use a transformer and some rectifier arrangement, and also this is kind of like a very robust solution. Okay, transformers have been here for more than 100 years, and rectifiers are also very robust thing, very robust power electronic component. And so therefore this solution is also very popular not only in drives, but also suppose if we build EV charging. Okay, suppose we want to make large scale megawatt level charging infrastructure where we want to charge batteries. Okay, so we have to it's not a residential battery charging, it is a like a commercial large scale battery charging, which is going to become popular very soon. Okay, for example, in India, if we adopt more and more electric vehicles, it is not possible for us to kind of like charge in our houses. Suppose we are adopting large scale a fleet of buses where this needs to be charged simultaneously from the grid, and this needs to be charged fast also. We cannot keep on charging for very long duration, 12 hours, 16 hours, we cannot charge. We have to kind of like charge it very quickly also. So in that case, we need this kind of rectifiers. And one of the solutions that is possible is like based on multi-pulse transformer with a rectifier arrangement. Okay, and this is something which is very much economical and ready to use, although it has its own drawbacks. One of the drawbacks is that the size of this transformer is quite big. Okay, this kind of multipulse transformer has one drawback, is that these are all 50 hertz transformers, and so the size of this transformer is very big. Okay, and so people have actually thought of something else which is also called a smart transformer. Okay, which will not we will not cover it in this course, but smart transformers are power electronic based transformers where we actually do this isolation. Here the isolation is done using a 50 hertz transformer, but in a power electronic transformer or a smart transformer, we convert this AC into a DC at first, and then we have a high frequency DC-DC converter or a high frequency DC-DC conversion. Okay, and then when we go for the high frequency DC-DC conversion, the size of the transformer becomes substantially smaller, very small size. We may be like 10% of the size of this kind of a transformer for the same power rating. So the transformer size becomes much smaller. But the problem with that approach is, again, it's number one, much more costly than this, and it's a much more elaborate solution. This is a very simple solution. Okay, and so because you are going to high frequency, you are first converting AC to DC, then you are going for high frequency, you are using a lot of power electronic devices, switching them. So this is something which one must weigh, or which one must consider which solution is to choose when we want to rectify. Okay, so now let us do some solved examples on what we have learned so far on multipulse rectifiers and also the Fourier series analysis of waveforms. Let us take the first problem. Okay, the first problem here is asking what is the peak-to-peak ripple in an 18 pulse rectifier. Okay, now we have studied 12 pulse rectifier, but the question asks 18 pulse rectifier. Now one of the things, okay, this is the peak-to-peak in an 18 pulse rectifier. This question is not complete in the output voltage. So the question should be in the output voltage. Okay, output voltage of, right. So what we have understood from the 12 pulse rectifier output voltage, we understood that in a 12 pulse rectifier there are such kinds of 12 lobes, right? So there are 12 lobes in one fundamental cycle. Okay, this is omega t, and there are two, so 1 2 3 4, you can count them. So there are total 12 lobes, right? And so we also understood that in a 6 pulse, so this is 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so this is 12 and this is 2 pi, this is the fundamental. Okay, so this is the output voltage, right? So there are 12 lobes. We also understood that in a 6 pulse rectifier, the number of lobes in this 2 pi or in the fundamental cycle will be like 1 2 3 4 5 6. Okay, 5 6 in the this one. Okay, similarly in an 18 pulse rectifier, okay, the number of lobes will be 18. Okay, extrapolating the same concept. So we said that if you have a 24 pulse rectifier, the output voltage will have these 24 lobes like that. So what happens is the output voltage becomes closer and closer to DC. Okay, so you see here in the 12 pulse, okay, if there are 12 such lobes, then we have understood, we know that suppose this value is 1, okay, this is 1 per unit, and this, therefore this duration will be 360 degree by 12, which will be roughly which will be equal to 30 degrees, right? So therefore we have seen that this duration is 15 degree. Okay, this is 15 degree, and so if this point here is 1, if this point here is 1, this is basically cos 15 degree, right? Okay, so and this value will be something like, we have to check, I roughly vaguely remember this will be like 0.95 or something like that. Okay, so yeah, we have to see. I forgot cos 15 degree. Just hold on for a second. Cos 15 degree was 0.96. Okay, so similarly, so therefore the peak to peak ripple here will be, okay, 1 minus cos 15 degree or 0.04. Similarly, in a 6 pulse rectifier, we have seen if you have 6 pulse rectifier, this angle is 60 degree. Okay, and so if this value is 1, this value will be cos 30 degree, right? So which is equal to 0.866. And so the peak to peak ripple, that means this peak to peak ripple here will be about 14%. Okay, so you can see that the ripple is decreasing 14% to 4%, and so extrapolating this way, so we are actually getting closer and closer to the DC. Okay, so what will happen with 18 pulse? So in an 18 pulse you will have 18 lobes. Okay, 18 such lobes in a time period of 2 pi. Okay, and so therefore I can find out what is the maximum and minimum value of this waveform. If I take the maximum as 1, this value will be 10 degree. Okay, so it is 20 degree, one lobe is 20 degree, so this is 10 degree, so which means this value will be equal to, here this value will be cos 10 degree, right, which is 0.015. Here I have written it. Okay, so therefore the peak to peak ripple in the output voltage is only 1.5%. so you see here we are going, here this is 14%, 6 pulse, then we are going to like 4%, so this is 4% here, and this is here 1.5%. so we are getting closer and closer to the DC. Okay, so therefore the peak to peak ripple, okay, this is not 14%, this is 4%. Okay, this is 4% here. Okay, so the peak to peak ripple is improving. So this is what we have been asking, what is the peak to peak ripple in an 18 pulse rectifier in the output voltage? The answer is 1.5%. Okay, so this is, so when you go with a higher pulse rectifier, the output voltage becomes closer and closer to DC, but there is the second advantage, and that second advantage is the input current. Okay, in the input current, that is what you have written here, input current will have harmonics of the order 17, 19, 23, 25, like that. Okay, so whatever is the pulse number, yeah, so in plus minus 1, that is the place where the first set of harmonics will come. Okay, in a 12 pulse rectifier, the first set of harmonics, in a 12 pulse rectifier, the first set of harmonics come like the play if you analyze the input current harmonics, it will come at 11, 13, 23, 25, like that. Whereas in an 18 pulse, it will be like this. No, not like this. So wait. So it will be like this. 17, 19, 35, 37. Okay, like this it will go, not 23 and 25. So in an 18 pulse rectifier, 17, 19, 35, 37, 50, 53, 55, that way the harmonics will be present. Okay, so this is one example which we can cover. Okay, now the second example. So consider the input current waveform drawn by a rectifier as shown. You can see this is the rectifier as shown, right? So what is the peak 10th harmonic current if I equal to 10 ampere and alpha equal to 15 degree? Okay, so this is the first question. Now observe this waveform and see what type of symmetries we have. In fact, we have a half wave symmetry in this waveform. Okay, so here you can see that you can take this f theta is equal to minus of f of theta plus pi. So you take any value here, okay, and you will get exactly the same value, but with a minus sign, right? With a minus sign at theta plus pi. And one of the properties of this half wave symmetry is that no even harmonics can be present. So therefore 10th harmonic will be 0. Okay, fine, this is easy. The second question is, what is peak third harmonic current? Now in order to understand the third harmonic current, then we see that we have to recall one formula, okay, which we have derived during the lectures, and that formula is something like this. Okay, this was the formula of the magnitude of the nth harmonic. Okay, 4i by n pi cos n alpha. Okay, here alpha is this alpha, so the general formula is like 4i by n pi cos n alpha sin n omega t. Okay, for any nth harmonic, any n, right? So ft, n equal to odd. Okay, so therefore you put it here, right? You put it here into this and put n equal to 3 in this expression, and straight away you find that the answer is something like, you put the values here and it will come out to be 6 amperes. Okay, magnitude of this. One thing that you will also observe here in this case, that here we have put cos 3 pi by 12 because we have put basically cos 3 alpha. Okay, now you can see here that if alpha is equal to 30 degree, okay, if this value of alpha equal to 30 degree, then what happens? Then this value will become equal to 0, right? So the third harmonic in this waveform, the third harmonic will remain absent if alpha is equal to 30 degree. Okay, so that is something which we can also observe, right? So this is the second problem. Now consider the third problem. Okay, problem 3. Now here we are given a waveform like this, right? And we have to answer certain questions. Now here this is a voltage waveform and there are notches in the waveform. Okay, so these kind of notches are used sometimes in something called as selective harmonic elimination while working with voltage source converters with low switching frequency. Okay, but that is the application part of it. Let us just do it from a pure problem solving approach. Okay, so consider given here V equal to 100 volt and alpha equal to 30 degree. Okay, so in this waveform you can see there are notches. So this was plus here and then the notch came here and then again plus and then a notch like this. The question is, what is the DC component in the waveform? Of course, if the waveform is symmetric about the y-axis, right, you can see it is perfectly symmetric, right? So here you see this one this one and this one and this one, all these are perfectly symmetric with, you can see this pi, this angle is pi here, pi minus alpha, this is pi plus alpha. And so by observation, you can just see by observation, you can say that the DC component in the waveform is 0. Okay. Now, second part. What is the fundamental peak value of inside this voltage given this condition 100 volt and alpha equal to 30 degree? So we need to find out what is the fundamental component in this waveform. In order to solve this problem, there are many ways you can do. Like analyze it by doing the integration. Okay, you can do that. It's absolutely possible, but it will be taking some time. Okay, we can do it in a faster way. Okay, and we can do this by dividing the waveform into different parts and using some of the results that we have already seen earlier. So what will happen here? So what we have done here is that this is the final waveform which we have obtained, but we see that this is the basically subtraction, okay, subtraction of two waveforms. So this is the first waveform and this is the second waveform, and 1 minus 2 is basically equal to 3, which is the third waveform here. Okay, and how are we doing this? You see here, this is a full square wave. The first waveform is a full square wave, and here in the waveform 2 we have introduced this notch at the angle alpha, right? But note that the amplitude of the second waveform is plus 2v and minus 2v. Okay, so which means that here from this waveform I am actually subtracting plus 2v like this. Okay, if I subtract 1 minus 2, I am subtracting this portion from the waveform, correct? And once I do that, I get to this final waveform. Okay, so this is something which I observe in the waveform. So now what I will do is I will now find out the Fourier series of this waveform and this waveform and subtract them. Okay, so we have already seen that we have just hold on for a second. First term, okay, so what is the general expression? The general expression is like ft that I shown last slide, 4v by n pi cos n alpha. Okay, this is the expression for this kind of a waveform, okay, where this amplitude is v. If you take this as the v amplitude, then this is the general expression of any quasi-square wave. Okay, if you can recall that one, then I can use this one. Okay, so for the first waveform, you see this is the expression for the first waveform. So for n equal to odd, so n equal to odd, we have 4v. So this one 4v is there, so 4v by n pi sine n omega t, here alpha equal to 0 degree for the first waveform, f1. For the second waveform, you can see here this second waveform, we see that this is again 4v into 2 by n pi, because why it is 2? Because you have this thing 2v here. Okay, so 4v into 2 by n pi cos n alpha, because alpha is here indicated, alpha and pi minus alpha here. Okay, so 4v into 2 by n pi cos n alpha sin n omega t, right? Again n equal to odd. So this is the Fourier series expansion of the second waveform. And then what we do is we subtract second from the first term. So then what I get? 4v by n pi 1 minus 2 cos n alpha, okay, sin n omega t. So this is the expression for this waveform. Of course, you can get it from other ways by doing integration and finding out the values at all points on this waveform, but this is a easier way of doing things. Now in this case, therefore, now we put the values of alpha and v which we have been given, okay, and substitute the value for n equal to 1 because we have asked the fundamental peak value, and so this value will come out to be 93.2 volt. Okay, so this completes another problem. Now let me do one more problem. Okay, the input current of a waveform has the following expression. What is it? It has 10 root 2, this is the amplitude. Then you have 2 pi ft minus pi by 6. So this is the, so then there is 2 pi 250t and 2 pi 350t. So which means this is fundamental, this is fifth harmonic, and this is seventh harmonic. Okay, of course they have certain amplitudes. This is 10 root 2, this is 5 root 2, and this is 2 root 2. Okay, so now the question is okay, and the fundamental frequency is given as 50 hertz. This is the fundamental. Okay, 2 pi f is 50. The question is, what is the THD of the current? Okay, very simple, and you can find it out very quickly. So the what is the formula for the THD? THD means the contribution of all the harmonics divided by the contribution of the fundamental, right? So you have this I2 square, I3 square like this divided by I1. Okay, in this case we have taken the RMS values, correct? So I1 has an RMS value of 10, whereas the fifth harmonic has an RMS value of 5, the seventh harmonic has an RMS value of 2. So therefore this THD straight away, if you see, this is 53.85%. Okay, now this example, although it seems to be very trivial, but it has actually some practical connections. Okay, generally when we do experiments sometimes on this kind of PWM rectifiers, we need to find out the harmonic spectrum as well as we need to find out what is the total harmonic distortion of the input current. Now in an experiment, this can be done quickly by analyzing the input current waveform and putting it into something called as a power analyzer. So something called as a power analyzer. Okay, power analyzer is an instrument that can actually take the input current and will immediately give you the THD and all the harmonics, the full all the harmonic magnitudes, okay, and angle. It will give all the values. Okay, but this one is very costly. Okay, this is the problem. This instrument is actually very costly. Now the other way, if you do not have a power analyzer and if you suppose have a simple DSO, okay, DSO means digital storage oscilloscope, you can actually find out the THD of the input current or the harmonic spectrum of input current by using the formula which is shown before. So in DSO, what you do is that you can actually, suppose this is the current, input current, you can store this current by sampling the current, okay, by sampling, digitally sampling this current and storing it into a memory, okay. So if your sampling frequency is very high as compared to the fundamental or the frequency up to which you want to get the harmonics, then so generally these DSOs are like sampling at megahertz, several hundreds of megahertz, okay. So it is very fast actually. So when you sample that at that frequency, then this current waveform you can easily analyze, okay. And suppose you take this waveform, you put it in a memory and then write a program, okay, write a program in a software, okay. Typically we many times use MATLAB, okay, because MATLAB has certain inbuilt functions that actually can analyze. So it has an inbuilt function called FFT, fast Fourier transform, and then by putting that command into that block of memory which contains the so the sampled value of the signal, okay, you can actually get all the harmonics. And also if you modify the code, you will also get the THD, okay. You can use, instead of MATLAB, other free softwares are also possible. There are many free softwares that can take this sampled value of the signal and can do an FFT on it and can immediately give you, because it is the FFT is a general code, okay. This is a series, this is a line of, there are few lines of code, and you will get the harmonic and the THD directly. So this is a cheaper alternative, okay. This is a cheaper alternative as compared to this costly power analyzer. Of course the power analyzer is very useful because on the run, when you are doing the experiment, you just put your current signal into the power analyzer and it will immediately show all the harmonics, sometimes in a graphical way, nice presentation. But if you do not have the power analyzer, then this is a cheaper alternative, okay, which you can do it yourself in the lab, okay. So with this we actually end the small tutorial or some additional problems that I wanted to discuss. So anyway, we have covered one of the solutions here, and in the next class onwards we will start looking into other solutions like voltage source converters and what is their impact and how do we so basically we will start with the what is called as PWM rectifiers from the next class. Thank you.